Chemical screening is the process of identifying specific amine groups within a sample. Amines are organic compounds derived from ammonia, and their classification determines how they will react during the synthesis of more complex molecules like isothiocyanates. Understanding amine reactivity is crucial for the pharmaceutical industry. Isothiocyanates are vital intermediates used to produce drugs and agricultural chemicals, making the screening of starting amines a foundational step in industrial chemistry. The isothiocyanate group consists of a nitrogen, carbon, and sulfur atom double-bonded in a sequence. This specific arrangement creates a highly reactive electrophilic carbon, which is the key to its utility in chemical synthesis. Amines are categorized by how many hydrogen atoms of ammonia are replaced by organic groups. Primary amines have 2 hydrogens, secondary have 1, and tertiary have none. This hydrogen count is the primary constraint for isothiocyanate formation. The formation of the isothiocyanate double bonds requires the loss of 2 hydrogen atoms from the starting nitrogen. Therefore, primary amines are the ideal and most common precursors for this specific chemical transformation. Secondary amines present a significant constraint. Because they only possess 1 hydrogen atom, they cannot undergo the final elimination step required to form the N=C=S group, resulting instead in stable dithiocarbamate salts. Tertiary amines lack any hydrogen atoms attached to the nitrogen. As a result, they cannot form the necessary intermediates for isothiocyanate synthesis, acting only as bases or remaining unreactive in the mixture. Let's look at methylamine, a simple primary amine. With 2 hydrogens available, it reacts efficiently with carbon disulfide and a base like triethylamine to produce methyl isothiocyanate, a common soil fumigant. Aniline is an aromatic primary amine. Despite the electron-withdrawing nature of the benzene ring, the 2 hydrogens on the nitrogen still allow for the successful formation of phenyl isothiocyanate, though reaction conditions may vary. In the case of diethylamine, a secondary amine, the reaction stops early. It forms a dithiocarbamate salt. Without a second hydrogen to eliminate, the process cannot reach the isothiocyanate stage, demonstrating a clear structural constraint. Even among primary amines, constraints exist. Bulky groups, like the tert-butyl group, create steric hindrance. This physical crowding slows down the nucleophilic attack, requiring longer reaction times or stronger catalysts to form the isothiocyanate. When screening amines for synthesis, chemists first determine the substitution level. Once a primary amine is confirmed, they assess steric bulk and electronic effects to choose the best reagent, such as carbon disulfide or the more reactive thiophosgene. The choice of base is a critical constraint. A base is required to strip away the protons during the reaction. If the base is too weak, the reaction stalls. If the solvent is incompatible, the amine may not dissolve, preventing the reaction entirely. To summarize, the primary constraint for isothiocyanate formation is the amine structure. Only primary amines provide the 2 hydrogens necessary for the double bond elimination process, while secondary and tertiary amines lead to different products or no reaction. Quick question: which of these amines can successfully form an isothiocyanate? The answer is isopropylamine. Because it is a primary amine with 2 hydrogens on the nitrogen, it satisfies the chemical requirements for the reaction. By understanding these structural and electronic constraints, chemists can effectively screen amines and predict the success of isothiocyanate synthesis, paving the way for new innovations in molecular design. Generated by Vision Solve AI.